All right, welcome everyone. Today we have Nikola Milicevic from Pennsylvania State University. And Nikola will be speaking about homotopy, homology, and persistent homology using Czech's closure spaces. If you have minor clarification questions, feel free to ask them via chat or unmute yourself in the middle of the talk. But if your questions are more involved or philosophical in nature, please wait until the end. And with this, Nikola, you have the stage.
Thank you, Tesh, and thank you for inviting me to do this talk. So, like Tesh says, this is the title of my talk: Homotopy, homology, and persistent homology using Czech closure spaces. This was work for my thesis together with Peter Bubenik. So everything I say is going to be joint work with him at the University of Florida. Let me just give you some basic motivation for this work. So I work in topological data analysis, and a typical setting we have in topological data analysis is we have some sample of a space. For example, we have a circle and you have some sample points, maybe 8 roots of unity or something. And you would like to infer something about the sample from the space. And typically the way we do that in algebraic topology is we look at maps between spaces, and you have an unknown space, you have a known space, and maybe you can infer something about the unknown from the known if we have some map. The problem when we do data analysis is we have this point sample. There's only one continuous map from the circle to the point sample, it's just a constant map. So the way we try to fix that is we start constructing an increasing sequence of simple complexes typically. So eventually you can imagine that these points at some scale will get connected, and then you will have maps between, and you can say, okay, the homology at certain scales is the same as a circle. Maybe at later scales, the whole circle gets filled in. But Antonio Reiser asked a different type of question in his paper, and it was, what if we actually just modify the definition of continuity and we allow certain maps from the circle into this discrete space to be called continuous? Can we still define some invariants like homology, homotopy, and so on? And can we infer those invariants via these new continuous maps? So for example, like if imagine you split the circle into 8 different pieces and you map each piece to its nearest neighbor on these roots of unity. So typically that's not a continuous map, but what if we allow that to be a continuous map? So it turns out that something called Czech closure spaces, or some people also call them pretopological spaces, are the perfect setting for doing this. And they are a generalization of topological spaces. So a lot of the statements I'll be making, if you're familiar with them for topological spaces, I'm going to be generalizing those statements to pretopological spaces. And what are these things? So you want to characterize them in terms of a closure operator. And remember, for topological spaces, you also have a closure operator. And this closure operator satisfies some axioms. You want the closure of the empty set to be empty. You want it to be expansive. So, the closure of the set is always bigger than the set. You also want the closure to respect unions. And there's an additional requirement for topological spaces is that you want the closure operators to be idempotent. So we get closure spaces, Czech closure spaces, by just dropping the last axiom of idempotency. How can you maybe immediately apply this to data analysis? Well, if you think of a graph and you define its closure of a vertex to be its adjacent vertices via edges, typically this will not be idempotent, right? Because you can just keep growing the edges more and more as you keep applying the closure operator. So that's the application in mind. And we can also define continuous maps between these spaces, and you just want, for every subset of your domain, you want the image of the closure to be contained in the closure of the image. And this is actually equivalent to, if you restrict to topological spaces, this is actually equivalent to the standard definition of continuity. However, the standard definition of inverse images of opens doesn't really extend to closure spaces. It's not equivalent to the statement. So you want to take this statement as your definition of continuity. And let me just give you some example. So an example of a closure space that's not a topological space is if you, let's say, take the Euclidean space and You just thicken every set by some real number r. Just by looking at the distance to the set, you include all those points in the closure, and you can immediately see that you can thicken twice, and that's not the same thing as thickening just once. So it's clearly not idempotent. So there is no topology. There's no topological closure you can put on this space that's going to give you this is not a topological closure. Okay. So this is how you should think about these things. They're kind of expansive. They allow you to model proximity relations. There's a nice way to define new closure structures from old closure structures. And it involves something similar to the definition of neighborhoods in topological spaces. So remember, I have these three axioms or three conditions here for a collection of subsets containing a point in your space. And these are very much similar to the collection, the neighborhoods of a point that you have in topological spaces. So you want the collection to be non-empty, and you want the point to be contained in every element of the collection. And for every two elements, you want always to find a third element in their intersection. So it's kind of like a basis almost. Remember, in the case of topological spaces, you can actually characterize the closure of a set using neighborhoods. You can say the point, one valid definition of a closure in topological spaces is a point is in the closure of a set if and only if every neighborhood has of that point has a non-empty intersection with your set. And you can actually just use that here in this theorem as the definition. Whenever you have a collection of subsets satisfying these properties, you can define a unique closure operator from those collections. So in particular, when we have products of spaces, there happens to be two canonical closure structures you can put in the product. One is just the regular product closure, which you also have for topological spaces. And you set these collections of neighborhoods to just be rectangles around each point, that come from the underlying spaces. But there is this other inductive product closure that does not really appear, and you never hear about it in points at topology. And instead of looking at rectangles, you're looking at these crosses. Okay, so you take a neighborhood from X, and that's like the horizontal part of the cross, and then you take a neighborhood from Y, and that's your vertical part of the cross, and you define these to be your collections, and you take the closure they generate, and you call it the inductive product closure. The reason you don't hear about this in topological spaces is because you can have two topological spaces, and their inductive product is almost never a topological space, so it leaves the category. Okay, and a few more definitions. I'm gonna consider the category of directed graphs to just be a set together with a reflexive relation. And a category of undirected graphs is just I'm requiring the relation to be symmetric. Okay, so you think of the relation as the edges. We can also define symmetric closure spaces. You say closure space is symmetric if for every point in your space, whenever you have that X is in the closure of Y, you have that Y is in the closure of X. And we also call a closure space quasi-discrete if you can write the closure of every subset as just the union of these atomic closures of singletons. It's a quick observation that the category of directed graphs is just isomorphic to the category of quasi-discrete closure spaces. And the category of undirected graphs is the same as the symmetric and quasi-discrete closure spaces. And the proof is straightforward. So suppose I start with a directed graph XE, and how do I define a closure space from this graph? Well, I can define the closure of every vertex in the graph to just be its adjacent vertices. You can reach you can reach them from X via an edge. And then the closure of an arbitrary subset is just the union of all those closures for each vertex. There is an inverse operation that goes the other way. So starting with the closure space, how do you define a graph? Well, you define that there's an edge between x and y whenever y is in the closure of x. So these operations are kind of inverse to one another. So that's how you get this isomorphism. Okay, so that's nice. So now we have that closure spaces. It's a very big category, and I think you have topological spaces, you have directed graphs, you have undirected graphs, and you have things outside of those as well. For the rest of the talk, I want to fix some notation. I want to give some symbols to specific graphs I'll be considering in this talk. So by J, I'm just going to call the clique on two vertices. So just this simple undirected graph here. And you can think of it as a closure space where the closure is the indiscrete closure. So everything is in the closure of everything. So the closure of, let's say, the point 0 is the whole set, and the closure of the point 1 is the whole set. Okay. Also, I want to define this J plus and J minus directed graphs, and they're subgraphs of this one. You just delete one direction. So J plus, you have this edge going from 0 to 1, and J minus, you have the edge going from 1 to 0. You can think of these as closure spaces. If you define the closure on J plus to be the closure of 0 is 0 and 1, and the closure of 1 is just 1, and you do the opposite for J minus. So you can see these are just the two functors that I had in the previous slides. And what's interesting here is that if you consider the standard unit interval, there's actually a continuous map in this sense of closure spaces, or actually just topological spaces, from the unit interval into one of these graphs. I define just everything strictly less than 1/2. I define it to be mapped to 0, and I define everything about 1/2, including 1/2, to get mapped to 1. One thing to note is that these are topological spaces. These closures are pretty simple, so you can check that they're idempotent really quick. So you can actually just use the standard definition of continuity, and you can actually pretty fast deduce that the only open sets in J plus are just 0 and the whole set. Those are the only two open sets. So to check continuity, you just need to check that the inverse image of 0 is open and that the inverse image of the whole set is open. And okay, so that's how I define them. So this map is continuous. And furthermore, if you consider the set theoretic identity map from J plus to J, okay, this is a subgraph, so it's going to be continuous, just as a graph morphism too. Now I remember I had these products of closure spaces. What do these products mean in the language of graph theory? So we have this regular categorical graph product, which is you insist that there's an edge between xy and x prime y prime, if and only if there's an edge between x and x prime and y prime. But there's also this Cartesian graph product where you add just the additional requirement that instead of just being an edge here, they actually have to be the same, or the other two have to be the same. So maybe this is a bit too much to parse just looking at the definition, but let me give you an example with the picture. So suppose you have, actually before that, I have this lemma that, the categorical graph product is actually just the product you would get by doing the product closure between the two graphs, if you think of them as closure spaces. And this Cartesian graph product would be corresponding to the inductive product of closure spaces. So let's look at an example. So if I have these two directed graphs, remember I denoted this by J plus and J plus. Their Cartesian graph product is just this square without the diagonal. Whereas their categorical graph product is you have to add the diagonal. The symbols are kind of meant to represent that. You have this cross, so it implies you have diagonals. Here you have like a box without the diagonal, so there's no diagonal. So it's supposed to be very intuitive, the symbols at least. Okay, and now that I've set up product operations and I fixed these canonical small graphs I want to consider, I would like to think of those graphs J plus and J and just the unit interval as interval objects in my category. and I have these product operations, and I would like to define some homotopy theories using the intervals and products. So I'm gonna call a closure space an interval object if I can have these if it has two distinguished points. I'm gonna call them 0 and 1. A morphisms of interval object is just, it's a map, so that, you know, it's a continuous map between closure spaces, but you need to send the 0 of one to the 0 of the other and 1 of the other to the 1 of the other. So if my tablet was working properly, what I would draw here for you today would be just the example I had on the previous page. I would have a map from the unit interval into J plus that maps 0 to 0. That's nearest neighbor map that I had, and that maps 1 to 1. And I would also have the map from J plus to J, just the inclusion map. Those would be examples of these interval morphisms. Okay, and so this is nice. And then when you have an interval object and a particular product operation, so by product operation, I just mean either the inductive product or the regular product. When you can think of the disjoint union of two spaces, just you have this inclusion map into the top and the bottom when you have this product with intervals. So you should think of this as a cylinder object that you can use to define homotopy theories. So okay, now when I have two maps within closure spaces, I have a particular choice of interval k and a product operation. I can define a homotopy relation to be the equivalence relation generated by diagrams of this form. So this is very standard when you have a cylinder object. You know, you have two maps between x and y, and you want to identify one of the maps with the bottom slice, one of the maps with the top slice, and you say they're homotopic if you can extend the map to the whole cylinder. Okay. But now you see we have, in topological spaces, we typically just consider the unit interval and regular product, but here we have many more choices for intervals and products. I wanted to just make an observation that this inductive product closure is always finer than the regular product closure, meaning that the identity map from this space to this space as a set theoretic map is always continuous. And that just follows from the definition, because, you know, rectangles are bigger than those crosses. So it's straightforward from the definition. But in particular, this means that the set of maps from x cross y into z is always, so every map, if you have a space z here, let's say, it would be much nicer if I had a tablet, but if I had a map into space z, I could always precompose with this identity map to get a map from the inductive product into that new space z. And this is just an example to tell you how weird this inductive product closure can be. So this is a typical function we typically show students when introducing them to calculus in multiple variables. You know, this map is not continuous at 0. It's a piecewise map, but it's not continuous at 0 because you know, you can take the limits across the x and the y-axis and you get the limit to 0. But if you take the limits across the diagonal or something, you get what, 1/2 or something in this example. But that's not a problem if you consider the inductive product closure on the real numbers, because a neighborhood of 0, 0 in the inductive product would just be a cross. So you would just be taking limits across the x or y-axis. That's the only thing you're allowed, and those agree. So there's no problem with continuity of this map. So it's a very weird operation. Now, once I've set this up, so I have these two product operations. I know that one is finer than the other. So meaning that, you know, you can always induce maps from one to the other. And if you have a morphisms of intervals between K1 and K2, then you can actually deduce an implication between the corresponding equivalence relations of homotopy. So for example, suppose you start with two maps that are K2 tensor 2 homotopic. So you have this space here, and then you have the cylinder object here, and you can extend the map here. Well, because you have that this product is finer than this one, you have this kind of natural transformation here, this square. And you also have a map between the intervals k1 and k2 that you assume to have, this H. So you can just pull back all these maps from this cylinder to this cylinder. And then you get that if F and G were K2 and tensor 2 homotopic, they would also be K1 and tensor 1 homotopic. And the lemma, just as a reminder, remember that I had these maps between the particular interval objects of interest to me. I have this map from the unit interval into J plus, and then I have a map into J. So then we have this corollary immediately that you have the following strict, well, it's not necessarily clear that they're strict, but you have these implications based on the previous theorem, how these different homotopies relate to one another. So for example, this J regular product homotopy implies all the other homotopies. And not only that, but it's actually maximal. So meaning that if you try, this is the finest homotopy relation you can define in the category of closure spaces. Any other potential homotopy relation you define, this one will imply it. Okay, so that's what I mean by maximal. So there could be potentially other homotopy theories you can define, playing with various notions of intervals and products, but this will always be at the top. Okay, so that's I don't think I'm going to be able to show that in this talk. It would require some work, but it was a pretty neat result, I think. Okay, and so I would draw some examples if I had the pen. But what do I mean by this object? This is just J inductive product with itself. So if you think of a line, product with a line, this is the undirected graph. It would just be the square without the diagonals. So this is contractible with respect to this homotopy theory, but it's not contractible with respect to this homotopy theory. So that shows you that this implication is strict. And you can come up with the, and you can also consider the directed case. It's analogous, and therefore this arrow is also strict, and you can actually show that all these arrows are strict. We have examples for all of them. Okay, and yeah, it would be much nicer if I could draw this, but it is what it is. Okay, so now suppose I have this interval object and I consider a product with itself n many times, either the regular product or this inductive product. So I get this kind of cube, which each side is like a k, which is this interval. So I can define cubical homology. I can define the front and back face of this cube, just like you would do for regular cubical singular homology for topological spaces. And then you can also define, so a cube would be just a singular cube would be a map from this cube into your space, and you would call it degenerate if one of its front faces is equal to one of its back faces. Okay, and then you define a chain complex of these singular cubes where you take all these singular cubes and you quotient by the degenerate ones. And this gives you a chain complex, and you can define a boundary operator in the standard way, which is just alternating sum of differences of faces. And, this is a chain complex, this is a boundary operator, so you get a homology theory out of it. So let's start counting. We had, so far I'm considering 3 choices of intervals, this J, J plus and the unit interval. And I have 2 choices of product operations. So I get 6 homology theories immediately just by doing this. And this is for cubical stuff, but cubes typically have simplices as subspaces of them. So for example, if I had J plus, regular product with J plus, I could imagine that this directed graph is what I would call a 2 simplex. It lies, I take it to be this one, or maybe it's this one. The same thing can be said for the undirected case. So this is J, regular product J. And then, for the regular case of the unit interval, you also have the regular triangle. So if you consider these objects to be your simplices, you can still consider maps from these simplices into your space. And then I apologize, this should be a J here, not a K. But you take the alternating sum of restrictions to when you delete vertices from the simplices, and this gives you a boundary map. And so then you have a chain complex, and then this is a boundary map. So you can define these singular simplicial homologies, but you only have them for the regular product, okay? Because remember, when I was considering the inductive product, this diagonal does not exist here, okay? So you only get 3 singular simplicial singular homology theories out of this. You don't get the ones for the inductive product. But you can show by using standard arguments from Eilenberg and MacLean using acyclic models that these cubical and their corresponding simplicial homology theories are identical. Okay, so you might think you actually have 9, but you only have 6 homology theories that are different. You can go a step further. You can ask, do these homology theories satisfy analogous results from algebraic topology? Do you have like Eilenberg standard axioms for them or something like that, or other theorems, Hurewicz theorems, Van Kampen theorems for homotopy groups you can define, and so on. So I'm going to define K tensor homology theory. So it's going to depend on a choice K and a product operation. It's the standard definition. Every statement is the same. Excision statement is the same. You have a closure operator, so you can analogously define an interior operator, so you can define an interior cover of a closure space. So then you have a statement for excision. And everything else is the same. You have a long exact sequence of a pair. The only thing that's different from the standard definition of these axioms is that now the homotopy relation depends on this interval K and the product operation tensor. So what we can show is that, okay, for any choice of the interval K I was considering, J, J plus, or I, and the regular product, you have a homology theory. Everything else seems to work for the other theories, but I can't get excision to work. Okay, excision is a bit tricky, so it's still open if the other ones satisfy some version of excision or something. And there's other theorems I'm working on, Kunet theorems and so on, but that's still work in progress. And now coming back to topological data analysis, how should we try to incorporate this machinery that we developed? So suppose you have a metric space. I kind of alluded to this in one of my first examples when I was considering the Euclidean space and thickening by some R. So if you have a metric space, you can define a closure operator by considering thickenings by some epsilon. And a nice observation is, if you have these two metric spaces, and if you thicken if you put the closure on one or both of them to thicken by 1, that's actually the product. The closure on the product, the regular product closure, will be just thickening by 1 in the L infinity metric. You could maybe guess that the inductive product is thickening by 1 in the L1 metric. You need to make some assumptions for that. You need to make some assumptions about your spaces. It's not always true. What is always true is that it's always finer than the thickening by 1 in the L1 metric. But to get the other direction, you need to make some assumptions that are necessary. Okay. And also wanting to incorporate this furthermore into TDA. Suppose you have a closure space and suppose you have an abstract simplicial complex. There's some corresponding functors between the category of closure spaces and abstract simplicial complexes. So I'm gonna call one of them VR, standing for Vietoris-Rips. So it's the collection of all finite subsets of X, so that they're contained in the closure of each one of their points. Now, if you take the closure that it's one of these coming from a metric space, you would just be saying that this simplex is always contained in the epsilon ball around each of its vertices. So this recovers the Vietoris-Rips definition. This is the Vietoris-Rips complex when you consider these closure operators. Similarly, you can also define the Čech complex that extends the definition of the Čech complex. And it's all finite subsets of X, so that there is a point in X, possibly outside of that subset. Okay, so it's X is in X. It doesn't have to be in sigma, but you want there to be this point so that your simplex is contained in the closure of that point. So this extends the Čech complex definition. And you can also go the other way from simplicial complexes to closure spaces, where if you start with a simplicial complex, you can define the closure on it. The underlying space is still the same. It's just the set of vertices you had, but the closure of is kind of extending that definition for graphs that I had. You know, instead of looking at just the edges, you look at all the simplices that contain that point, and you take their union. And the nice observation here is that there is some adjunction between these functors. So the Vietoris-Rips functor is actually a right adjoint to this functor G going the other way. It's not clear the Čech complex has any adjoint or anything like that. We tried to make it work, but we couldn't. But not only that, but these functors are very nice with respect to various homotopy theories you can define on the two categories. So remember, for simplicial complexes, typically what one considers like a notion of homotopy is like contiguity. So you say two maps, simplicial maps are contiguous if when you take any simplex in X, their images under F and G, and the union is a simplex in Y. These functors are nice because, you know, if you have a J1 regular product homotopy, sorry, this should just be J, should not be J1. If you have a J regular product homotopy in the category of closure spaces, then both of these functors, Vietoris-Rips and Čech, will send it to contiguous maps. So those will be contiguous. And the converse is also true. If you start with contiguous maps under the functor G, they will be sent to J times homotopies. Okay. I wanted to do some examples for some of these homology theories. So if you have a finite metric space and you consider the unit interval J, and you consider the thickening by R, then this homology is just the homology of the Vietoris-Rips complex at scale R. So that this was shown by Boris Goldfarb. He phrased it in a different language, not in the language of closure spaces, but you can reinterpret his results to say this statement. And then if I wanted to look at H1 with respect to J and the regular product of just J with itself and the inductive product, so it's this square without the diagonals. From the above theorem, you know, this should just be the same as the Vietoris-Rips on this square. So it should just be Z. If you just define CR to be 1, and this is like a metric space where the distances between each one is 1, the weight on all the edges is 1. And then I argued before, I had it in one of the examples, that this space here is contractible with respect to this homotopy theory, so this should be 0. The second, the third item, this is just the directed analog of that above picture. I'm just replacing J by J plus, so it's just the directed analog. So I would just put directed edges here instead, and you would get the same statements. And you could ask the question, okay, so why should I bother with these inductive products, cubical homologies? It seems that they don't satisfy excision. So like, are these other ones better when you consider the regular product? Well, the answer is that these inductive ones seem to be more discriminative. So for example, if I change my graph a bit, so let's say I flip this edge and I flip this edge, so I get this one. So this is my Y. It turns out that these inductive homologies actually can differentiate between these two directed graphs. Okay. But if I restrict myself only to the regular product, they would be the same. these homology theories cannot differentiate between these two graphs. However, these inductive ones can. Okay, one of these homologies is 0, and the other one is just z. So it seems that these inductive ones can be used to detect finer structures, maybe. Okay, and there's a lot of work that people have done over the years, over the last 3 or 4 decades in applied topology. That this is probably not even the full list, but this is the best I could do to find. So people have considered various homotopy theories in different settings: directed graphs, digital images, undirected graphs. So Anton Dochterman, then Helen Barcello and Reinhard Labenbacher, Antonio Reiser extended this regular notion of homotopy from topological spaces to closure spaces. But people have also worked on various notions of homology theories. Yeah, so I can't give credit to everyone because it's a very, very long list. But yeah, ask me more at the end if you want more references. Now I wanted to move to the topic of persistent homology. And for that, remember in the regular setting, for persistent homology, typically we have this increasing sequence of topological spaces, filtered topological spaces, so we can also define filtered closure spaces. And it's just a functor from some partial order, when you think of it as a category, to closure spaces, but you want to send all those maps between in the partial order, you want to send to monomorphisms. So we have this category of filtered closure spaces, and some examples. For example, suppose you have a set and you have some one parameter family of closure operations indexed by P on the set, so that the closure indexed by P is always finer than the closure indexed by Q whenever P is less or equal than Q. Then this collection forms a filtered closure space. But here, notice that the maps going forward, typically in the setting of topological spaces, the maps are inclusion maps. Here, all the maps are set theoretic identity maps. You're not changing the underlying space. The underlying space stays fixed. What you're changing is the closure structure on the space. But if you wanted to get actual inclusion maps into bigger sets, you can always consider the setting when you have a map from your closure space into some partial order, and then you can take the inverse images of down sets. And this gives you an increasing filtration of the space you started with. So this gives you actual inclusion maps as well. And then if we pick one of our homology theories and we compose the homology functor with this filtered closure space, we get persistent modules and persistent homology from this setting. And one thing we can do is we can extend the Gromov-Hausdorff distance from metric spaces to R filtered closure spaces. R is just, the real line. The way you can think of this is that you can embed metric spaces into R filtered closure spaces just by taking P to be, P is the real numbers, and then these closures will be just thickenings by epsilon. So you can embed the metric spaces in this category. And then you can extend the definition of Gromov-Hausdorff distances, the definition that involves using correspondences. You can extend that definition to define a distance between filtered closure spaces. And we have a stability theorem that says, okay, you have two filtered closure spaces, you take homologies, either one of these homologies, doesn't matter the choice of interval or the choice of the product, and you consider them in some degree J. The interleaving distance between them is always bounded by 2 times the Gromov-Hausdorff distance we define. And then some personal passion project of mine is to make sheaf theory work for closure spaces. So just a reminder, you have a sheaf of abelian groups on a closure space X is going to be a functor from the open sets. So this is nothing new, okay? Edward Čech defined this a long time ago, and it just, it's just a natural extension from the definition from topological spaces. And but it doesn't seem to be very useful for undirected graphs, at least when you restrict to them, because for this undirected graph, you can quickly compute that the only open sets are the empty set of the whole space. So it's not a very this category of open sets is very small, so it doesn't really allow you to do anything finer than just considering the if you're dealing with the indiscrete topology or something like that. However, it turns out for the directed graphs, you can actually have a much bigger collection of open sets. And it turns out, so I didn't talk about this, but there is a functor from closure spaces to topological spaces. So you can always make a closure space into a topological one, and it's called topological modification. Now, when I restrict myself to the subcategory of directed graphs, every directed graph you can think of it as a pre-order. Every directed graph is just a reflexive relation. This topological modification would just be the transitive closure of that, because when you add transitivity, you've got an idempotency of the closure. You remember what's going to make it topological is if you have that c squared is equal to c. So once you add that, whenever you have an edge between these two and then you add this edge, it's always going to be idempotent. Okay. But the nice thing about this topological modification functor is that it preserves the collection of open sets. So you can actually just see what the open sets here are just based on what the open sets here are. And this is a pre-order, so you can just put the Alexander topology on it, which is equivalent to it. So the open sets are just the down sets. So the open set here would just be this singleton, then it would be these 2 points, and the whole space. So they would have 4 non-trivial open sets in this example. And then, if you have a map between closure spaces, it is always true that inverse images of open sets are open. What's not necessarily true is that that requirement, inverse images of open sets are open, is not enough to guarantee continuity with regards to the definition I gave you of continuous maps. But because you still have this, that inverse images of opens are open, you can still define the direct image and inverse image functors on sheaves. Recently, actually just this week on Wednesday, Antonio Reiser put out a different approach to sheaf theory on closure spaces. That's called Grothendieck topologies and sheaves on Czech closure spaces. It's on archive right now. I'm still reading it, so I don't know much about it, but it seems to use a much finer collection than just open sets. So it might be possible to actually consider interesting sheaves on just even undirected graphs under this approach. So I'm very excited about that. And I wanted to just give a quick summary of this work. So we have some underlying sample space, and it's typically in applications, it's not going to be a topological space, because, for example, here you see, if you think of this directed graph as if you think of the closure that you can define from its edges, B will be in the closure of A, and C is in the closure of B, but C is not in the closure of A, so the operation would not be idempotent. So this will typically not be a topological space. But you can still consider all these different maps, or from these, you can think of them as probes, from these directed graphs, undirected graphs, or you can actually, if you want to work in the continuous setting, that's allowed too. We know exactly what it means for a map to be continuous from here to here or from here to here. You can define all these homology theories, define your persistent homology. It's also possible to define homotopy groups in a similar fashion. So some future work I would be considering is maybe trying to interpret, to see if there's Hurewicz theorems, von Kampen theorems in this setting. I would like to see if there's a relation to magnitude homology. Can I maybe interpret magnitude homology as a particular homology theory of closure spaces? And there's also this path homology by Alexander Grigoryan and his collaborators that I would like to see how this fits in that setting. And these are some references. So that our paper is on the archive right now. some more work by Antonio and the book on check closure spaces, which has everything you would ever want to know about check closure spaces, 1,000 pages of beautiful text. That will be all. Thank you.
Feel free to unmute yourself to thank Nikola. Questions for Nikola? Okay.
Can I ask one question? Probably like like very simple question. So what are the the morphisms of the category of p-filtered closure space X?
All right. Yeah. So they're functors. So it's natural transformations.
Yes.
Functors.
So it seems like for each like coordinate, you want it to be like inclusion as well. Somehow. I don't know.
So I don't think you need to, so if you think of the vertical maps are just monomorphisms, sorry, horizontal maps as monomorphisms.
Yes.
I don't think there's any requirement on the vertical ones to be monomorphisms.
So because
they just need to commute, those squares need to commute.
But like for the like the category of closure spaces, there are like two data like for the object, right? So one is the space, the other one is the closure operator. So somehow, I think for the vertical maps, so you want like to, I don't know, to have some property like order preserving or something like that.
Yeah. So you want if you have X and Y are those filtered spaces, you want vertical maps from XP to YP or XCP to YCP, and that has to be continuous.
Oh, okay. Yeah. Okay, that makes sense. Thanks.
I'll ask one question. So can you go a couple slides back? It was like right before you moved to persistence, where you had examples. Yeah. So yeah. So in the second point, you said that the one homology there is 0 because that space J box 2 is contractible in that homology. Is that right?
Yes.
Could you maybe shine some light on how, like, is there a way to like imagine this notion of contractibility?
Yeah. So just think of multiplying. So you have, let me do the undirected case, but it's the same reason why this is 0. Okay.
Sure.
This is just the undirected case.
Yeah.
So just imagine like multiplying this thing by the interval J with respect to this product. So what you would get is a cube without any diagonals.
Right.
So that will be your cylinder. And what you want to do on the bottom is you just want the identity map. On the top, what you're going to do is you're going to move this point down here and this point down here. Okay, and then you have to do an extra step. Then you have to add another level, do it again, and then you just contract this point to this point. You can't do it in one step, unfortunately.
Sure. Okay.
Yeah. And the same thing is the directed case. It's the same thing for the directed case.
Okay. Got it. Thank you. Other questions for Nikola? If not, let's thank the speaker again. I'm going to stop recording now.